In 6.4, we're going to examine a concept called trees. And the definition is that it is a graph with the smallest number of edges that can allow all vertices to be reached from all other vertices. In other words, this means a graph must be connected and circuit-free. That's key. It can't come back on itself to be a tree. So which of the following are trees? So this one, I have the ability to get from one to another, one vertex to another by accessing through the edges. So this is actually, yes, a tree. This one here is not. And the reason why it's not, because there is a loop in there. C, that's not the least number of edges because I have a parallel edge in there. So I'm going to say nope. We have a parallel edge. And then D actually is a tree. In fact, it looks like a tree. Believe it or not, E is a tree. F is not because it has a circuit. And then 9 is not because it's disconnected. Let's see here if I can get that written. Not sure if I have much room. Nope, disconnected. There we go. Now the other thing I like to do is to show you patterns, and maybe you'll see this. If I count how many vertices I have here, I have 4, and my edges are 3. So that is one that is. This has a vertex of 1 and an edge of 1. This one has a vertex 4, meaning I've got 1, 2, 3, 4 of them, and it has 4 edges. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 vertices and 14 edges. This one has 1 vertex and 0 edges. This one, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. And 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. And then on this one, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 edges. So one thing you'll notice is that there's a pattern with the ones that are trees, where there's some kind of special relationship between the number of vertex or vertices and your edges. All right, so let's go ahead and use a tree in a way that we can do some decision making. Here we've got an example where we've got an orientation week for college and a student has to take a placement test. So as part of the placement test, there's 2 scores. There's a score on part 1, which exists here, and then there's a score on part 2. And based on how they do on each of those parts depends on what math they will be enrolled in. So I'm going to use my first one with blue here. So a student who scored 9 on part 1 and 7 on part 2. Well, 9 on part 1 falls right in there. So I'm going to go from that first score over to this next box. And then part 2, they got 7. That's greater than 6. So they're actually going to be enrolled in Math 110. Now let's take a look at another one. Student who scored 12 on part 1 and 4 on part 2. So 12 would have them go up here to the greater than 10, which would bring us to this part. And then they score a 4 on part 2, so that's way less than 10. So that also puts them at Math 110. I want you to go ahead and pause this video and see if you can do that third one on your own, and then we'll get back together. All right, so this third one, we scored an 8 on part 1 and a 9 on part 2. 8 falls right within here. So I'm going to take that path and then a 9 on part 2. That follows right in here. So we're also looking at Math 110. So all three of these actually end up in Math 110. So here it starts to talk about the relationship between the number of vertices and the number of edges. If n is a positive integer, then any tree with n vertices has n minus 1 edges. Let's take a look at these up here. See how that one was a tree? And you have 4 vertices and 3 edges. Here's another tree, 15 vertices, 14 edges. Here's another tree, 1 vertex, 0 edges. And then I don't think we have any more trees up there, right? So what you're going to do is just list your vertex. So I have 1, 2, 3, 4, 5. And then my edges are 1. So of course, no, this is not a tree. This one has vertex of 5 and edges of 4. Absolutely, that's going to be a tree. This one, we know it's not because it has a circuit. But let's go ahead and see if with just the numbers, it'll take care of us. So we have 5 vertices and then 1, 2, 3, 4, 5 edges. So we don't have the fewer edges that we need. Okay, so that's how we can tell if it's not a tree, is by outlining how many vertices and how many edges we have and making sure they're 1 apart where edges is 1 less.